Okay, welcome to another video on control system stability. We shall again use Routh stability criteria to find the stability system. So these are the few basics you should know. Okay, let us continue with the things what we have discussed in the last video. Okay, this is what the characteristic equation of the previous system with poles at s plus 2, s plus 6 and s plus 8 as my open loop poles. We found this as the characteristic equation and wrote the Routh's array. This is Routh's array, and we also try to find out, okay, when does this term become 0, for what value of k that becomes 0. We took that as k margin here. If the value of k margin is 1120, if it is, if you substitute this value as 1120, then this entire term will become 0. So then you have a 0 0 as the elements of this particular row. So then we have to consider an equation called as auxiliary equation, which is a row above the zeroth row. So this is 0, this is 0 when k is equal to 1120. I'll consider an auxiliary equation which is exactly a row above this. A row above this is my auxiliary equation, which is now equal to 16a square plus 96 plus k margin. This is k margin equal to 0. Then I'll write it is s square 16 equals minus of 96 plus 1120. So what is this 96? Okay, then this will become, okay, 1 second. It is 1120 plus 96 is 1216. So s square is actually minus divided by 16. If you actually find the roots of s now here, s is equal to plus or minus j. So it is now under root of, sorry, under root of, that is, this is what out, okay, under root of 1216 divided by 16. 1216 divided by 16, which happens to be 8.7. 8.7. You can see this is the same value what we got in the previous video when we actually found the roots using calculator. So we actually got this as one of the root, which is 8.71, which we got here also, The meaning of this particular process is, whenever a particular row of Routh's array, if all the elements of a particular row become 0, then we will have a special case. So what is a special case? If it is 0 0 means then poles are on imaginary axis. So that is the clue that we're going to get. So the poles, if it comes onto the imaginary axis, then the entire elements of the Routh's array become 0. Then how do we find the pole position? For that, I have to consider the auxiliary equation, which is a row above that 0th row, which we wrote it here, and then we are solving for the roots of that auxiliary equation, which happens to be the closed loop poles for value of k is equal to 1120, which means that system is now oscillatory. The value of k is 1120. That's what we found here. So initially when we are just trying to randomly give different values of k, you can see when we actually give it as 5000, the roots have gone to right hand side. So how many roots are there? There are actually two roots. So okay, this is one onto the left hand side. So this is plus 3.3 plus j 12.46 and plus 3.3 minus j 14.64. So I have two roots on the right hand side of the S plane if the value of k is 5000. So can we do the same thing here? Can we just actually find out how many roots will be there on the right hand side when k is equal to 5000. So when k is equal to 5000, you can see here it is 1, here it is 16. Then what will be this? It is 116 into 76 minus 96 into 5000 into 5000 divided by 16, that will be minus 29,000 something. So it is minus 20. It's actually, we are looking at the sign is negative, and here it is again 5096. So you can see there is a plus here, there is a positive here, here it is negative, here it is positive. Now we just travel from here to here. This is plus, this is plus, so no sign change. This is plus and this is minus, there is one sign change. This is minus, this is again plus, so there is a second sign change. So plus to plus no sign change, plus to minus one sign change, minus to plus another sign change. You have two sign changes on the first column of your Routh survey from S power 3 to S power 0. So how many sign changes? There are two sign changes. So number of sign changes is nothing but number of closed loop poles onto the right hand side of the screen. So what does this mean is, so this means that on right hand side of the S-plane you have two closed loop poles. I don't know where exactly they are, but I can able to get there are two onto the right hand side. So that's what is there here. You can see for k is equal to 5000 are the poles onto right hand side of the screen, because there are two poles onto the right hand side of the, there are two poles. So out of three poles, two are on the right hand side and one is on the left hand side. System is unstable. System is unstable for this case. Suppose if you take k is equal to 1000, suppose if I take k is equal to 1000, then this is positive. So all are positive. This is positive, this is positive, this is also positive, this is also positive. So no sign change. When there is no sign change means no poles onto the right hand side of the screen. So system is stable. Let me again tell. If you take the value of k as 1000, if you take the value of k as 1000, so what is this? What will be this value? It is 16 into 76 minus 1096. Can you see it is, sorry, it is 16 into 76 minus 96 plus 1000, sorry, 90, okay, 1 second, it is 96 plus 1000. Can you see it's a positive number? So this is plus 120 by 16, so it's a positive number. This is positive, this is also positive, so this will become 1096. You just don't worry about the magnitude, okay, the values, you look at the sign. So all the signs are positive. When all the signs are positive, no sign change, so meaning that no roots onto the right hand side of the S-plane. So system is stable if you have no sign changes. If you have sign changes, then those many are there on right hand side. If you have this 0, then there is an auxiliary equation, then the poles are there on imaginary axis, then you have to find the roots of the characteristic. So let us find one more such. So to the same, we will add a 0. So we had it as k, this is GFS is equal to k by s plus 2, s plus 6 and s plus 8. Let us add one s plus 1, 0 let us add. So we know that, so this is s cube plus, for simplicity I have written the same thing, it is s cube plus 16s square plus 76s plus 96 plus k into s plus 1 is my del of s. Correct? This is my del of s. So let me just rewrite this. It is s cube plus 16a square plus 76 plus k into s plus 96 plus k equal to 0. Let us find, does this system is stable or unstable or so. So it is s cube is equal to, so what is this? This is 176 plus k, and this is 16, this is 96 plus k, then it is 76 plus k into 16 minus 96 plus k divided by 16. This is 0. This is this into this minus this into this. It is 96 plus k. This is s for 1. This is s for 0. What I have? I have this. So I have this term here. So it is 76 plus k into 16 minus 96 plus k. If you can see here, for any values of k between 0 and infinity, this term is always positive. Give value of k as 1, give value of k as 100, give value of k as 1000, give the value of k as maybe 20,000, whatever value of k you give, it will be always, because this is always greater than this. So naturally, this term is always positive for all values of k greater than 0. Meaning, this is positive, this is positive, this is also positive, and this can never be negative, because for any positive values of k, this is also positive, meaning that the first row of your Routh array will never become, there will be no sign changes. It is plus to plus, plus to plus, plus to plus, no sign change. So system is stable for all values of k greater than 0. Then I'll call it as absolutely stable. Absolutely stable. So how does a system which was conditionally stable has become stable? Because we have added a 0 at s plus 6. Sorry, at minus 1 I added a 0. At minus 1 I added a 0. So that's why system has become absolutely stable from conditionally stable. This is how we can able to very easily say for any values of k, system is not at all becoming unstable. There is no question of roots going on to right hand side of the screen, because for any value of k, this can never become negative. So let us again take the same whole portion. Let me add a 0 onto the right hand side. Let us see what happens. Let us add a 0 onto right hand side. So now let me just make this k s minus 1. So just for simplicity, s plus 2, s plus 6, s plus 8. So this is my g of s. So what I'm trying to do, I'm trying to add a 0 onto right hand side. Instead of s plus 1, I'm adding it as s minus 1. Let us see what is, does the system will become stable, absolutely stable, or absolutely unstable, all the stuff. So now the equation is s cube plus, let me again rewrite that. It is 16s square plus 76s plus 96 plus k into s minus 1 equal to 0. So it is now s cube plus 16s square plus 76 plus k plus 96 minus k. Fine. So now I will write this Routh array now. Interesting to see what happens to this. This is s cube, s square. You can see now this is 1, 76 plus k, it's alternate powers of alternate coefficients of s. It is 16, it is 96 minus k, so it is now 16 into 76 plus k minus 96 minus of k by 16 and 0, and this is 96 minus k, correct? See now, so now what you have? You have 16 into 76 plus k minus 96 minus k, okay, by 16. Can this value become any way negative for k values of greater than 0? For any positive values of k, this is always positive. This is always positive. So this is positive, this is positive, this is also positive for all k values of greater than 0. But how about this? The value of k is greater than 96. So then this is becoming negative. Assume that it is 97, then it is minus 1. So one sign change. So if the value of k is greater than 96, then the system is what? System is, now it's only one pole. You can see how many sign changes there are. It is plus to plus, plus to minus, and then plus to, sorry, plus to plus, plus to plus, plus to minus here. Only one sign change. Only one sign, sorry, a sign change. Since there is only one sign change, of course, system cannot be oscillatory. System has to be oscillatory, means two poles should come onto the imaged axis. Only now system is oscillatory. If the system has only one pole, then system is on the okay, system has a closed loop pole on the real axis. Now the system is not oscillatory, but system is, for values of k greater than 16, system become unstable. For the value of k is equal to exactly 96, pole will come onto the origin. Pole will come onto the origin. Now the system is not oscillated. The system is not oscillated. But system is not stable, and if the value of k is, greater than 96, then it is unstable. This is okay. For k value of, this is 96, less than 96 means stable. This I'll say it is not stable, not stable, not stable. And it is also ensure that, of course, the system, of course, we know that when I say not stable, of course, if it is okay, let me not say it as not stable. When it is on the math axis, it will have a DC output. It will have a DC output. The oscillations are not there, but the output is a DC signal. Output is a DC signal. I can still say the system is stable because it is giving a finite output. Suppose if it has got two poles on the imaged axis, then it is oscillatory. If it is only one pole, it is still stable. If it goes on to right hand side, it is unstable. If it is on left hand side, it is still stable. So with k is equal to 96, one pole is there on at the origin, at the bottom. That's what is this saying. So because I have kept one pole onto the right hand side of the screen, system is stable for k values less than 96 or less than or equal to, I'll say this is stable. This is stable for k value of greater than 96. System is unstable. There is no question of oscillatory here. Why? The poles are not coming onto imaged axis. Only one pole will go to right hand side of the screen. I hope you're getting. You had three poles, minus 2, minus 6, minus 8. Only, of course, you have a 0 here. You have a 0 at plus 1. Only this pole is coming over here, and the value of k is 96. So system is still stable. If the pole come here, then it is unstable. So this is for a value of k greater than 96. For less than 96, it's on to the left hand side. But exactly 96, it's sitting on sitting at the. So that's about this particular problem. Now let us take another interesting thing and try to find out what happens now. Suppose if I take, okay, you can generate the problems of your wish. Suppose if I take closed loop poles at, let us take 4 roots now. It is s into s plus 2, s plus 3, s plus, let me take x plus 6, s plus 8, so that is easy for me to just do the calculation. So what is this? This is my g of s, and your h of s is equal to 1. Then what is del of s? So del of s is easy for me to write. It is now s to the power of 4 plus, let me just find out, it is 16 s cube plus 76 s square plus 96s 96s plus k. This is my characteristic equation. So it is same 16, as we had it as 16 s square 76s plus 96. Now it is fine. So write the roots for this. So find k margin. So that system is oscillating. How do you find? So this is now s to the power of 4. Now your calci you cannot find. S cube. This is 176. This, and then k. Correct? S power 4, s square, s power 0. Now it is 16, 96, 0. What is s square now? It is 16 into 76 minus 96 by 16. Next it is 16 into k, minus 0 by 16. So this will become k. This is 0. So how much is this? So this is now 16 into 76 minus 96 divided by 16 is 70. This is actually 70. This is 70. This is now, let me write s cube. This is 70. This is actually k, and this is 0. Then what is s power 1? It is 70 into 96 minus 16 into k divided by 70, and this is this into this minus this is actually 0, 0. Then s power 0 is actually k. This is what we got. And here you have 1, here you have 16. This is positive, this is positive, this is also positive, and there is a possibility that this can become 0. That is 70 into 96 minus 16 into k margin is equal to 0. Therefore, k margin is uh, k margin is 70 into 96 by 16. It is 70 into 96 divided by 16. That is 4.4. K margin is 420. For a value of k greater than 420, then system will have, this is 0 0. When this becomes 0 0, I am going to have an auxiliary equation. A row above this is 70 a square plus k margin is equal to 0. Then it is 70 a square is equal to minus 420. Then s is equal to s square is equal to minus 420 by 70. Which is 420 by 70? 420 divided by 70 is 6. It is 6. So now it is minus 6. So S is equal to plus or minus J root 6 will be the frequency of oscillation. So if K is equal to, in this particular case, if K is less than 420, no sign change, stable. If K is greater than 420, two sign changes. See here, plus to minus, minus to. This is, if it is more than 420, then this will become negative. So till down here it is no sign change, plus to minus, and then minus to plus. Two sign changes. Two sign changes. System is unstable because two roots onto right hand side. If K is equal to 420, system is oscillatory at a frequency of root 6 omega, okay, root 6 radian per second. That's what is this. So S square is 6, where S will become root 6. So root 6 will be, so root of 6 is 2.44 radian per second. System will be oscillatory with a frequency of 2.44 radian per second, because poles will come onto plus J 2.44 and minus J 2.44 if the value of K is 420. Otherwise it's on left hand side, otherwise 2 will go on to right hand side if the value of K is more than 420. That's how you can able to find this. Now to this, if you add a 0, let us see what happens. To this, if you add a 0, so what you have, it is K plus 1 into S. This is now S, so I can write S into S plus 2, S plus 6, S plus 8. So it is now DFS. Adding a 0 to this fourth order system will make what? So it is del of S now. So again same thing. It is S power 4 plus 16 S cube plus 76 S square plus 96 S plus K into S plus 1 equal to 0. Equal to 0. So I can write this S power 4 plus 16 S cube plus 76 S square plus 96 plus K plus K. Correct? So now the roots are will be S power 4 S cube, it is now 176 K. Next it is 16 96 plus K 0. This is square is 16 into 76 minus 96 is K by 16. And then K 0. This is now S power 1. Is this into this, minus this into this. We have a K term now here. This is K, and what is this? This into this minus this into this. It is now, so okay. Let me just find out how much is this. Let me rewrite this. It is 16 into 76 minus 96. It is 120 minus K, okay, by 16 by 16. Okay, to 0. So then what is your S for one term? S for one term is, it is 1120 minus K divided by 16 minus of 96 plus k divided by this one 1120 minus k by 16. Okay, and then this into okay, then this is k. So okay, it's actually this into this and this into this is actually 0. So now what is this term? This term is this into this minus this into this by this. That's what it is. Next is this into this minus this is actually 0. What is S power 0 term? It's actually this into this minus this into this by this. So S power 0 term is actually S power 0 term is k 0 0. Now we are looking at this quantity. Now we are looking at this quantity. So here no need to consider this because now you have not all the terms are becoming 0. All the terms will become 0 over here. So all the terms will become 0 here because you have a 0 here, you have a 0 here. So now we have to look at 1120 minus k by 16 minus 96 plus k. When does this will become 0? So can I just simplify this? What is this now? 1120 divided by 16 is 70 minus k by 16 minus 96 minus k equal to 0. Correct, now it is minus 26. So it is minus of it is 16 volts plus it is 1.065 k. So now correct. So it is, let's see, or can I write this 1120 minus k minus of 16 into 96 plus k equal to 0, which is same as this. It is 1120 minus 16 into 96 minus of 17k equal to 0. So how much is this now? It is 1120 minus 16 into 96 is actually minus 416 minus 17k equal to 0. So minus of 17k is equal to 416. So k is equal to 416 by 17. 416 by 17 is 24.47. So k is equal to minus 24.47. System is having 0 0.